Okay, we're online now. Great. I would let now the participants in, if you agree. We wait about a minute or two, and then let's start. Okay, I welcome you on another edition, another webinar in for the framework of the YoungStatS project of the One World YoungStatS webinar series. The series is part of the YoungStatS project of Young Statisticians Europe in the framework of the FinStats Association. It is supported by the Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute of Mathematical Statistics. Today, we will talk about recent advances in approximate Bayesian inference with 4 excellent speakers: Lorenzo Pacchiardi of University of Oxford, Emilia Pompe, also University of Oxford, Łukasz Rajkowski, University of Warsaw, and Théo Moins of India, Grenoble, Rhône-Alpes. We have as discussant Julien Arpel, also of Inria, Grenoble, Rhône-Alpes. I hope you will enjoy the webinar, and I will just give the word to Lorenzo Pacchiardi, the first speaker, for his presentation, Generalized Bayesian Likelihood-Free Inference Using Scoring Rules Estimators. Lorenzo, please, the floor is yours.
Hi, everyone. Can you see my screen?
Yes.
Cool. Yeah, thank you very much, everyone, for coming, and thanks for the invitation to speak in this seminar. Yeah, I'm going to talk about my work on using generalized Bayesian inference techniques for likelihood-free inference problems. And specifically, I do this using some scoring rules estimators, but yeah, I will discuss everything in detail now. So first of all, just to give some background, what do I mean by generalized Bayesian inference? So I think everyone is familiar with the standard posterior. So let's say you have an observation Y, you want to get a posterior distribution on the parameters theta. So by standard Bayesian inference, this is proportional to the product of a prior term and the likelihood of the model. And if you want, you can write this expression as being the prior times the exponential of the log likelihood. So generalized Bayesian inference starts from this formulation and basically replaces the log density of the model by a generic loss. So this was formalized in very much detail in this paper in 2016. So as I mentioned before, you have a generic loss between, let's say, your observation y and the parameter theta. And you basically replace the log likelihood in the above expression by a negative loss, which is scaled by some parameter, hyperparameter w, which basically has the role of fixing the scale between the prior and the loss. So what is this quantity? What is this posterior? So if you want to understand what's going on, you can think of this as being an order coherent way to update beliefs about this quantity here. So let's say you are a Bayesian statistician and you consider Bayesian inference being a way to update beliefs about the KL minimizer between your model distribution and your true models, let's say. So in the same way, you can consider this quantity as being a way to update beliefs about the minimizer of this expected loss, where basically you consider the loss between the observation and the parameter theta, and you take the expectation with respect to the true generative distribution P naught. By order coherent, I just mean that if you have multiple observations, the way, let's say, the order in which this observation arrived to you doesn't matter at all. So if you have y1, then y2, or if you have y2 and y1, then the final result doesn't depend on the order in which you update your posterior, your belief, let's say. Right, so what's the advantage of this strategy? The advantage is that this is a very general formulation, and specifically the parameter theta doesn't need to parameterize a model. So theta can, it can be any generic quantity for which you're able to define a loss between the observation and this quantity. So you don't need to write down a probabilistic model P theta in general. The biggest drawback is that you need to tune this scalar quantity W here, which gives some troubles in practice. Right. Now I will briefly recap what do we mean by likelihood-free inference. In likelihood-free inference, we are interested in the setting in which we have what we call an intractable likelihood model. So let's say you have an intractable likelihood model with a parameter theta. Basically, this means you can very easily simulate data from it. So you can generate, for each value of theta, you can generate a simulation X from the model. But you're not able to evaluate the posterior density, sorry, the likelihood, not the posterior density, but the likelihood itself. But this means that it's basically impossible to get to obtain the standard posterior, let's say by MCMC or other ways. So likelihood-free inference approaches, what they do is they basically they are strategies which allow to get samples from an approximation of the posterior, which would be intractable otherwise. And the way they work is, in general, they rely on drawing simulations for the model. So let's say for instance, you will be running an MCMC chain, and at each step of the MCMC over theta, you will generate some simulations for the model and do some other computation, and eventually your MCMC will be targeting an approximation of the posterior. So what's the key idea which we had in this work? Basically, the key idea was to consider a generalized Bayesian posterior specifically for the likelihood-free inference approach, for the likelihood-free inference setting. So what's the special bit in this case is that our theta, the parameter theta, does parameterize a probabilistic model, P theta, which is our intractable likelihood model. And for this reason, we take a class of losses which basically depend explicitly on P theta, not only generically on theta. So basically, in the expression for a generalized posterior above, we replace the loss between y and theta by some other function S between the distribution P theta for the given theta and the observation y. So this class of functions is usually called scoring rules. But then we have another feature of our setting, and that's it. That's that we can only draw samples from our model. So we want to use some scoring rules for which easy estimator from samples are possible. So basically, in practice, you're not able to evaluate this quantity, but you will replace this quantity by an estimator, where the estimator is obtained by simulations from the model p theta. Right. So how does this play out in the real world, or yeah, more extensively? Basically, yeah, first of all, let me discuss a bit better what are scoring rules. So as I mentioned before, scoring rule is a function between a distribution and an observation y, and you can think of this as a penalty when you state a distribution p theta for an observation y. So when you have that, you can, let's say, if your data comes from another distribution p naught, which is a true data distribution, you can define an expected scoring rule by basically taking the expectation of this scoring rule with respect to y sample from the p naught, right? And there are two key properties of scoring rule. One is a scoring rule is said to be proper if basically this expected scoring rule is minimized in the first argument whenever the first argument is equal to the second, right? And strictly proper is a scoring rule for which this minimizer is unique. So basically, if we get back to the starting point of our discussion, which was this generalized posterior, where we had this exponential of a negative loss, now we will replace this loss by a scoring rule, right? And let's say you have multiple observations, y1 up to yn. So the posterior given all of these observations will be proportional to the prior times the exponential of this negative sum for all the observations of the scoring rule between the distribution of the model p theta at a given parameter value and the observation yi. Right. Some caveats which comes from using the scoring rule is that basically the prior which you are introducing here doesn't have the same meaning as the prior which you would be using in the standard for a standard posterior, right? By this I mean the prior, if you recall the original starting point of this posterior being a way to update belief about the minimizer of the unexpected loss. So this prior refers to this quantity, to the minimizer of this expected scoring rule. So the prior has different meanings for different choices of the scoring rule. And this is just a picture, just to understand more or less, let's say, the generalization levels. So you can start from the original base theorem, and there are some words where they introduce a power likelihood. So basically, instead of updating with the likelihood by itself, you introduce a power to the likelihood, let's say, in general, smaller than 1. Then a bit more general, we have the scoring rule based posterior, which is a subset of the loss based generalized posterior, where the loss is just replaced by the scoring rule. And then there is an even more general class of posteriors, which I won't talk about now. So right, let me give now some examples of strictly proper scoring rules. And why do I care about strictly proper? Well, it will become clearer later, but basically strictly proper scoring rule, a strictly proper scoring rule is one for which you're able to exactly identify when the model is matching with a true data distribution. So the most commonly used one is just the log score, which is just basically the negative log density. And as you can imagine, if you just insert this scoring rule in our formulation of the scoring rule posterior, what you get back is exactly the standard posterior distribution, the Bayesian posterior. A bit more, other choices are these two, the energy and the Kenneth score, and the expression now doesn't matter too much. What matters is that they are defined through expectations with respect to the model p theta. And importantly, well, the Kenneth score is associated to the to the squared MMD distance, which is a popular distance in machine learning literature between probability distributions. Right. So let's get back to the likelihood of inference setting. As I mentioned before, we cannot compute the score exactly, as we don't have the likelihood, right? First of all, so how do we go with this? So if you remember the expression for the energy score, which I've just shown, basically we have two expectations. So the easiest thing you can do is basically replace these expectations by empirical means. So instead of computing the expectation over the p naught over p theta through the model for a given theta, you can just generate a bunch of samples, say m samples, and you replace the expectation with the empirical mean. Right, and very similarly, you can do for the Kenneth score as well. So basically what we do is we run an MCMC chain, and at each step we replace in the scoring rule posterior, this scoring rule between p theta and y with this estimator. This basically leads to a pseudo-marginal MCMC framework where the target is this quantity, which looks quite ugly because basically the issue is that we are replacing, we are estimating a quantity which is inside an exponential. So by pseudo-marginal MCMC theory, we are targeting a posterior which depends on the expectation of the exponential of our estimator. But the good news is that these two, like let's say the pseudo-marginal MCMC target is very close to the true scoring rule posterior if the number of simulations goes to infinity, basically, if it's large. And this is stated by this theorem, which we show more in detail in the paper. Right. Well, if you are familiar with the likelihood free inference literature, you may realize that this is fairly similar to an approach which is called Bayesian synthetic likelihood. And this is actually a subset of our scoring rule posterior, where the scoring rule is actually chosen to be not strictly proper. And this leads to some issues, as I will show later in the experiment section. So, right, properties of the scoring rule posterior. I will just go very quickly on this because I don't want to go into detail for these theorems and stuff. So basically, we were able to show some unsurprisingly Bernstein-von Mises concentration. So the idea is that if the scoring rule posterior, let's say, is well behaved, and you have a unique minimizer, then you for the large number of samples, basically the almost surely the posterior converges to a normal distribution centered in the true let's say in the unique minimizer of the expected scoring rule. Right. And interestingly, a unique minimizer is, well, you have a unique minimizer whenever the model is well specified and the scoring rule is strictly proper. So this is one reason why strictly proper scoring rules are important. Right, so we've also shown a finite sample generalization bound. So this expression looks very intimidating, but basically what it is saying is it's giving a probabilistic bound on the distance between the posterior expectation of the MND distance from the minimum value that the MND distance can get between the model class and the true distribution, let's say. And as you can see, this bound is bound to say that this statement is saying that if the probability of this bound being larger than some quantity decreases exponentially with this quantity and with the number of samples, which is very interesting. Well, also this bound works in a misspecified case, and it basically, it leads to, it implies that the posterior will concentrate on a set of parameter values which minimize this MMD square. And also we have a very similar result for the energy score posterior whenever, well, under some other condition, let's say. Right, so here I will show you the first experimental results which we had. We consider this GNK model, which is a typical model in the likelihood free inference literature. And basically what we try to do is considering an increasing number of observations from 1 up to 100 and studying whether the posterior will concentrate or not. So if you can, as you can see, basically the energy score posterior, or I should say each column represents a different parameter, and we have 4 parameters in total here. So as you can see, the energy score and the kernel score posterior, even if a bit less, they tend to concentrate around the true parameter value, which is this green vertical line. While this other synthetic likelihood method, which, as I mentioned before, uses a non-strictly proper scoring rule, doesn't concentrate on the true parameter value. So this shows you why strictly proper scoring rules are important. We also have some outlier robustness of our method. So let's say you want to consider this perturbation model. So you imagine your model distribution is given by, let's say, p tilde with some probability 1 minus epsilon, where p tilde is the model you care about. And then with some probability epsilon, you get an outlier in location z. Right, so we consider the following definition of robustness in this setting. Basically, we compute the derivative with respect to epsilon, with respect to the proportion of outliers of the posterior condition on samples from this model. And then we say that the posterior is global bias robust. We define it as being global bias robust if this derivative is finite for all values for all locations of the outlier Z. So basically, we were able to show that if the prior pi theta is bounded over a posterior over the parameter space, then the scoring rule posterior is globally bias robust, following this definition for both the kernel score and the energy score under some condition. So what does it mean in practice? Like this experiment is showing this. So basically here is a very simple example. We are considering a normal location model. So we have our model being a univariate normal, where the parameter is just the location, the mean of the distribution, and we assume to know the variance, right? So in this case, we have 100 observations, and we have two, let's say, knobs you can tweak. One is the proportion of outliers, epsilon, and the other one is the location of outliers. So let me discuss about this figure in detail. So the first row, we are fixing the outlier location in z equal 10, and we are changing proportion from 0 up to 20%. And each column corresponds to a different method. So we have the standard Bayes posterior, the kernel score posterior, and the energy score posterior. And as you can see, when you increase the proportion of outliers, the standard Bayes posterior moves quite a lot, which is, it's expected. But the other two methods are very much robust to the proportion of outliers. And similarly, the second row we consider a complementary setup. So we have a fixed proportion of outliers, 10%, and we move the location of the outliers, so from 1 up to 20 in the data space. So basically, again, the standard Bayes posterior moves significantly, while the other two do not move. So this empirical result shows that they are strongly robust to outliers in the data. Right, so I'm almost done with my talk. I just want to do a quick recap. Basically, what we discussed is a new way to perform likelihood-free inference, and this way is based on generalized Bayesian inference, where we replace the loss in the generalized Bayesian inference formulation using the scoring rules. So this is fairly different from the standard likelihood-free inference techniques, because we do not approximate the standard Bayes posterior directly, as most of them do, but instead we consider a generalized posterior for which approximation for which sampling in the likelihood-free inference setting is fairly easy and which has strong robustness properties. As I mentioned, this has some useful properties such as outlier robustness, but it also has some consistency, meaning that if the model is well specified and the scoring rule is strictly proper, the posterior will concentrate on the true parameter value. So in practice, what we do is we use consistent estimators of the scoring rule from simulations, using simulations from the model in this pseudo-marginal MCMC setting. So that's basically the end of my talk. Here are some references if you're interested to learn more. And thank you very much for listening.
Thank you, Lorenzo, for the excellent presentation. I don't see any questions in the chat. I will just provide one very short one, and then I suggest we move forward. Could your approach be used in general, say also for the approximate Bayesian computation ABC approaches, in general for likelihood-free inference approaches? You mentioned Bayesian synthetic likelihood, naturally. So could this be used generally in LFI?
Yeah, so it's like, I think our approach is complementary to ABC. It's a very different formulation. So basically, in the ABC, you would have a different way to write the posterior, which is considering this acceptance rejection step. So it's not really, the two methods kind of match in a very specific setup where you have a single observation. You are generating a single simulation from p theta at each step in our case. But yeah, in general, they are a bit complementary. So yeah, and the main difference in practice is that for our setting, you need to generate multiple simulations from p theta at each step of the inference procedure, while in the ABC one, in most ABC formulations, one single simulation is enough.
Okay, great. Thank you. Thanks again for the great presentation.
Thank you very much.
Thank you. Let's move now to Emilia Pompe, who will speak about robust inference using posterior bootstrap. Emilia, please.
Hi, everyone. Can you all see my screen?
Yes.
Great. So my name is Emilia, and I'll be talking today about robust inference using posterior bootstrap. Many thanks to the organizers and many thanks to everyone who contributed to this work, in particular Pierre Jacob, Luke Kelly, and Judith Rousseau. I now work at Google, but the work that I'll be speaking about today was done when I was a PhD student at the University of Oxford before joining Google. So I'm really excited to be here today and come back to the academic world for a couple of hours. The algorithm that is basis for our today's talk is called weighted likelihood bootstrap, and it dates back to early 90s. It was designed to sample approximately from the posterior distribution. The algorithm proceeds as follows. We are given data x1 to xn from a likelihood f, and our parameter of interest is theta. Now, the algorithm first draws weights w1 to wn from the exponential distribution with parameter 1, and then take the argmax of the resulting weighted log likelihood, finally returning the samples. The paper about weighted likelihood bootstrap was published in JRSSB as a discussion paper, which means that everyone could submit their comment or opinion on this topic. And the opinions initially were mixed. So for example, someone said that WLB may enjoy some popularity. Another person said they feel a little uneasy about the paper. And I guess it's a lesson for us that sometimes we need to wait quite a bit until our work is properly appreciated, because around 25 years later, we started observing a huge resurgence of interest in this topic. So I've mentioned on the slides a couple of papers, and my work also follows this path, building on weighted likelihood bootstrap. I believe that largely this resurgence of interest stems from the fact that we've seen an enormous advancement in parallel computing, and samples in weighted likelihood bootstrap can be drawn in parallel. So what topics are we going to cover today? First, I'm going to say how weighted likelihood bootstrap can help us with misspecification. Then I'm going to cover different ways of incorporating prior information into weighted likelihood bootstrap. We will call it therefore posterior bootstrap because we incorporate prior information. And finally, I'll mention briefly some extensions to more complex models. Okay, so let us first define it formally what we mean by model misspecification. Suppose we have a model mapping from our parameter of interest, theta, to f of x given theta. But now the true data generating distribution, as denoted by p star, does not belong to this class. What happens then is that the MLE concentrates on, well, not on the true parameter, because we don't have a true parameter here, but on the so-called pseudo-true parameter, minimizing the KL divergence between P star and our family F. And we also need some notation that will be appearing throughout the paper. So first of all, I star is the Fisher information, and J star is the observed Fisher information evaluated at theta star. Now, it's important to remember that when the model is well specified, then J is equal to I. So what else do we know about asymptotics under model misspecification? Let us first look at the frequentist world. Asymptotically, after appropriate scaling, we have the following covariance matrix, so-called sandwich covariance matrix, J2 minus 1, I, J2 minus 1, and of course, the MLE concentrates around the pseudo-true parameter. Now let's look at the Bayesian world. Again, the posterior concentrates around the MLE or around the pseudo-true parameter, but the covariance matrix is different. So it's given by J2 minus 1. Okay, and what happens under weighted likelihood bootstrap and later under posterior bootstrap? Oh, sorry, I think yeah. Let me go back to the right slides. And under weighted likelihood bootstrap, again, the samples concentrate around the MLE, and the covariance matrix is again the sandwich covariance matrix. So what does it mean in practice? Well, let us remember again that for well-specified models, I is equal to J, so J2 minus 1 is equal to the so-called sandwich formula. For Bayesian inference, this means that credible sets are valid confidence sets in the frequentist sense when the model is well specified. So in practice, this means that suppose we generate 100 large data sets. And then if we perform Bayesian inference on it and construct 95% credible sets, and around 95 out of 100 times, we will cover the true parameter. For weighted likelihood bootstrap, this is true even when the model is misspecified for the pseudo-true parameter. Okay, so let us now do some expectation management around in what way weighted likelihood bootstrap can help us with model misspecification and what it cannot do. What does it mean that weighted likelihood bootstrap performs robust inference? The word robust means being capable of performing without failure under a wide range of conditions, but it doesn't mean under all conditions. So still the result depends on the choice of our likelihood function f. And in particular, the results will concentrate around the MLE, and the MLE depends on f. Now, it also doesn't correct for bias because it concentrates well around the MLE as Bayesian inference does. But still, it does help in many ways. So other robust methods, first of all, also concentrate around the MLE, but weighted likelihood bootstrap gives us the correct frequentist coverage. And this is not necessarily true for other robust methods, such as power likelihoods, for example. Okay, so now that we know the theory, let us look at an example. I said at the very beginning that one of the advantages of weighted likelihood bootstrap is that we can draw samples in parallel. It may or may not be quicker than running an MCMC algorithm until it converges. But now I'm going to show you an example where I really believe that using weighted likelihood bootstrap comes with a computational advantage. Suppose we're given a Poisson regression, as given on the slides. Now, Poisson regression may often be either over-dispersed or under-dispersed. If it's over-dispersed, we can alternatively use the negative binomial model instead of the Poisson model. But there is no simple alternative that captures both under-dispersion and over-dispersion. So what has been proposed is a so-called Conway-Maxwell-Poisson model. But it comes with two disadvantages. So first of all, it's computationally costly, and simple MCMC methods such as Metropolis Hastings cannot be used for this algorithm. And perhaps more importantly, there is a problem of interpretability. So it's no longer true that expected value of yi given x is what we are used to in the Poisson regression. So what else can we do? Let us look at this example. So we've plotted on the slides posterior distribution for coefficients from beta 1 to beta 7 on a generic data set. So it doesn't really matter what this means, but what's important is that we are dealing with an under-dispersed Poisson regression. So we've plotted three methods on the slide. So first of all, we have the Bayesian posterior for the Poisson model, Bayesian posterior for the negative binomial model. Well, the model is under-dispersed, so we don't expect the negative binomial to help. And indeed, it doesn't change anything. The results are pretty much the same. So it's just a sanity check. And we also see the red line representing the posterior bootstrap or weighted likelihood bootstrap. And what we can see that is that it indeed captures under dispersion. So the lesson from this is that one way of dealing with complex models is to, well, come up with more and more complicated computationally involved methods. But also sometimes what we can do is use a simpler model and account for misspecification by using weighted likelihood bootstrap. So that's the end of the first part. And now we're going to speak about incorporating prior information into weighted likelihood bootstrap. Let us look again at our very first slide. The paper on weighted likelihood bootstrap comes from the Bayesian community, and the word Bayesian appears even in the title of the paper. However, if we look closely, the prior information does not appear at all in the algorithm. And indeed, the algorithm does not have a mechanism of incorporating prior information. So my work focused on doing this, which means constructing an algorithm which first of all, can faithfully represent the user's prior beliefs about the parameter of interest and do it in a way that is mathematically principled. Now, we know that when the model is well specified, the Bayesian posterior does a pretty good job. So for well-specified models, we want our results to be as close as possible to the Bayesian posterior. Now, if the model is misspecified, we obviously want it to do a better job than what the Bayesian posterior would do. Okay, so the very first and actually quite simple idea that comes to mind when we think about incorporating prior information is to modify the function that we maximize. So instead of maximizing the weighted log likelihood, we now maximize weighted likelihood plus W0 times logarithm of pi. If the prior factorizes, W0 can be a vector, or in a simple version, it can be just a positive real number. Now, how do we set W0? So intuitively, we could think that it should be set to 1. And indeed, if we looked at the expected value with respect to the weights of the function that we maximize under W0 equal to 1, it's logarithm of the posterior plus a constant. But I'm going to try to convince you now that actually when the model is misspecified, we can do a better job than that, even though this intuition that W0 should be 1 is true for well-specified models. So let us look at the following misspecified models. We have data x1 to xn following the normal distribution with mean 1, and we have a normal prior on theta. Now the data is actually generated from a different model. It's generated from n theta sigma squared, and sigma squared is not equal to 1, so the model is misspecified. Okay, so if we want to perform weighted likelihood posterior bootstrap in this case, for the misspecified model, we would take the argmax of this function, which is equivalent to taking the argmax of the expression below. We just divided the whole expression by sigma squared. Now, if we knew the true model, we would instead take the argmax of this expression. So to match these two expressions, we need to set W0 to sigma squared. And it turns out this intuition is correct, but in order to have the mathematical justification for it, we need to look at it in more detail. Okay, so in order to analyze mathematically the impact of the prior on posterior bootstrap, we used so-called Edgeworth expansions. So the so-called first order Edgeworth expansion is equivalent to asymptotic normality. But higher order Edgeworth expansions extend the idea of asymptotic normality to higher order approximations. So if we look just at the first order approximation, the prior does not appear here. We know that a sample from posterior bootstrap for any choice of prior or any choice of W0 after appropriate scaling would converge to the normal distribution with the sandwich covariance matrix. This means we needed to look one step further at the second order Edgeworth expansion to see the impact of the prior. And so in practice, this means that we will first normalize the expression of interest and write down its density. Now its density is given by the density of the standard normal distribution times something, an expression which depends on our prior. Okay, so we found the second order Edgeworth expansion of posterior bootstrap with penalization, and it's given by the formula on the slide. And we compared it with the second order Laplace approximation for Bayesian inference. Now, when the model is well specified, and I'm sure you remember that the J is equal to I, so these two expressions, the only difference between these two expressions is W0. So this suggests that indeed when the model is well specified, we should set W0 to 1. Now, when the model is misspecified, we will again match the impact of the prior between posterior bootstrap and Bayesian posterior, but we use Bayesian posterior with a corrected scaling. And so there is some not very difficult algebra needed to find the result. I'm not going to show you here, but it's in the paper. And we get the result that optimally W0 should be set to the diagonal of this matrix. Now, as I said many times, I is equal to J when the model is well specified. So formally, we now have the result that W0 should be 1 for well specified models. And let's go back to our toy example. this formula would give us W0 star equal to sigma squared as expected. And so let us look at some simulations now. So we are looking still at the toy example with two different sigma squared options. So in the first case, we have a well-specified models, and as expected, we see that the smallest Kolmogorov-Smirnov dissimilarity between the base and posterior and a posterior bootstrap is when we set W0 to 1. Otherwise, it's when we set sigma squared to, when we set W0 to 2.8 as expected. Okay, so this idea, this including prior information through penalization works well for almost all priors, but not all priors. The problem appears when the prior explodes at the boundary of the set, which may happen, for instance, for some Dirichlet priors. What can we do in this case? Fortunately, there is an algorithm proposed by Fong et al. In 2019, which proceeds as follows. We first draw theta bar from the prior. We then generate capital T so-called pseudo samples with theta bar. Then we draw weights and take the argmax of the resulting expression when we are summing both the actual data and the pseudo observations. And the weight, the overall weight of our pseudo observations would be C. Again, so again, we have a question, okay, so how should we set C? Can we use a similar trick as we did with W0? The answer is, to some extent, we can. So again, we obtain the Edgeworth expansion for posterior bootstrap with pseudo samples. And unfortunately, what we get here is an alpha, which is an intractable constant. So this means that it's impossible to use a single value of C to scale all coordinates of theta appropriately. Unfortunately, there is also no generic default choice for C. And in particular, setting C to 1, which sort of worked well for W0 in the previous case, does not work at all as a good default here. But there is also some good news. So we know how to set C when we deal with conjugate priors in exponential families. So it turns out we should set C as the effective sample size when the model is well specified. And additionally, we should multiply it by W0 star that we had before when the model is misspecified. And I guess the biggest advantage of what we have seen so far about Edgeworth expansions is that other methods relying on weighted likelihood bootstrap or posterior bootstrap can be analyzed in exactly the same way. So using Edgeworth expansions with very much the same, maybe slightly adjusted calculations allowed us to understand the impact of the prior from the paper by Newton et al. And also from posterior bootstrap via pseudo samples from posterior predictive by Lydon et al. It also helped us understand whether the prior is incorporated correctly for hierarchical models, for posterior bootstrap for hierarchical models, and for posterior bootstrap with modular inference, which I will mention briefly in the next slides. And hopefully it will be also useful for analyzing other methods that will be appearing in the future. Okay, so now we're moving on to our last section, which is extensions to more complex models. So far, we've only looked at this very simple model that we have one parameter of interest theta and the likelihood f. And of course, in practice, we often use much more complex models. So we also developed posterior bootstrap for the following form of a hierarchical model. Suppose we are given k classes of data with likelihood f, and they are governed by parameter, each class is governed by its own parameter theta k. Now theta k is drawn from g of theta k given lambda, and lambda is the joint parameter over which we have a prior p. We proposed two versions of performing posterior bootstrap for hierarchical models when the number of classes is fixed and when it goes to infinity. And the advantages of this algorithm are twofold. So first of all, they can correct for misspecification because hierarchical models, as any other models, can be misspecified. And also it's an attractive computational alternative to Metropolis within Gibbs samplers that we'll typically use for that type of models. Now, another situation when we may want to use posterior bootstrap is the so-called cut posteriors or so-called modular inference. So let us consider the following model. We have data in the first module drawn from likelihood F1 and from the second module from likelihood F2, given parameters theta1 and theta2. Now, suppose that module 2 is misspecified. So in order to perform correct inference on theta1, we may want to so-called cut feedback from module 2 to module 1. That's why we call it cut posteriors. In practice, this means both for frequentist inference and Bayesian inference that we first perform inference on theta1 given the first module, and then perform inference on theta2 given data in the second module and theta1. So it's different from the regular Bayesian inference where we would make inference on all the parameters given all the data. And to give some more context, that is not something abstract, but something actually very commonly used in practice, let's give us some examples when we use modular inference. First of all, it's very common in so-called PK/PD models, also in Bayesian analysis after data imputation, because the first sort of part of inference is the imputation itself, and then the actual analysis. In various forms of meta-analysis as well, but perhaps the most important reason for using modular inference is causal inference with propensity scores. Suppose that we have several covariates, treatment or lack of treatment, it could be a binary variable, but sometimes also a continuous one, and the outcome. Now, in the first module, we regress treatment on the covariates to obtain so-called propensity scores, telling us how likely was an individual to receive treatment. In the second module, we regress outcome on the treatment variable and on propensity scores. That's why we have those two stages, or modular inference, in other words. And what we show in our paper with Pierre Jacob is that posterior bootstrap for modular inference comes with an additional advantage because it gives correct frequentist coverage. Okay, so to summarize what we've learned today, we have seen that posterior bootstrap can connect the advantages of Bayesian inference with the advantages of weighted likelihood bootstrap. Weighted likelihood bootstrap itself corrects for model misspecification, and it allows us to make computations in parallel. But on the other hand, so far there was no way of incorporating prior information or for using it for hierarchical models. And finally, we've seen that modular inference can be used itself to correct for misspecification to avoid propagating feedback in a wrong way, but we can make it even better if we used posterior bootstrap. Thank you. I'm giving here links to the papers that I was discussing today, and I'm happy to take questions.
Thank you. Round of virtual applause, naturally. Thank you for a great presentation. I encourage you to put your questions in the chat. Again, due to time limits, I will only pose one short one. In terms of the model misspecification, does this work for any type of model misspecification that could be possible, or are there just special types?
So that's a great question, and I get it a lot. So maybe let me go back to this slide where I sort of try to explain in what way it helps and in what way it does not really help. So first of all, it helps when we have wrong uncertainty, as what we have seen in the example with Poisson regression. And basically, the only thing, in some sense, that weighted likelihood bootstrap does is that it gives us the correct frequentist coverage. The credible sets are valid confidence sets in the frequentist sense. But it does not correct for biases. And the reason for this, sort of mathematically speaking, is that it concentrates around the MLE, which depends on our misspecified model F. So it may concentrate sort of on the wrong point. And basically for this reason, we looked at connecting modular inference with posterior bootstrap, because modular inference is something that can correct for the bias to some extent. And we, on top of it, perform posterior bootstrap to give the correct frequentist coverage.
Okay, great.
Long story short, it does not correct always for my specification. Does not solve all the problems, unfortunately.
Great. Thank you a lot. Thank you, Emilia, again. And I suggest we move now to Łukasz Rajkowski, who will speak about maximum a posteriori partition in non-parametric Bayesian mixture models. Łukasz, the floor is yours. Thanks.
Well, thank you very much for the invitation. I'm really flattered to be here with such talented speakers, and I'm really impressed by the previous presentations and certainly the presentation to come. Well, the problem I'm going to talk about, it concerns clustering. So every now one here knows certainly what it is about. Now, as our approach is Bayesian, so well, the unknown thing here is to distinguish homogeneous as homogeneous as possible groups within the data points. And now a bit unorthodox formulation of that, if we want to keep it Bayesian, is to treat this partition we want to infer about as parameter of my Bayesian model. So if this is going to be a parameter, I need some prior distribution on this parameter space, which is the space of all possible partition of data points. And there's a plenty to choose from. For example, one of the most classical ones is the Chinese restaurant process. For example, let us briefly remind what it is about. Say, want to compute the prior probability of this partition of numbers that you see. So imagine that the numbers are the customers in the Chinese restaurant. They enter the restaurant and sit by the tables. And every new customer chooses a table which is already occupied with probability proportional to the number of people sitting there. And he or she chooses a new table with probability proportional to alpha. So this is one of the most basic way to construct a probability on the space of partitions. So now we proceed with the usual Bayesian reasoning, as was already reminded in the Lorenzo presentation. We simply take the product of prior and likelihood, and well, we'd like to do some inference. And if we were to pick up just one partition, then one of the most natural idea you may think about is to pick the one that maximizes the posterior probability, which we'll call the maximum a posteriori partition. And this is simply the same as maximizing the product of the prior and likelihood, obviously. Okay, so now we already have an example of the prior distribution of this on the space of all partitions. Now, given the partitions, how can we construct the likelihood? How can we construct data points? So again, if we want the groups to be like homogeneous clouds in the observation space, a basic idea is to imagine that those clouds are normal or normally distributed. So we firstly, for each cluster, generate its mean according to some given normal distribution, and then within each group, each cluster, we sample from the normal Gaussian distribution with given mean and some covariance matrix. So this model I call normal Chinese restaurant process model, and it was the main object of interest of some time ago. And about this model, we proved some of its properties. For example, the MAP partition I've mentioned before in this model is linearly separable in the sense that every two clusters in the MAP partitions are separated by hyperplanes. Or in other words, you can say that the convex halves of those clusters in the MAP partitions are disjoint. Now, the question you may ask, if you already know that the clusters in the MAP partitions are the convex halves are disjoint, is to think about how this clusters behave as you increase the number of data points. Say you may, for example, misspecify the model. Your MAP procedure is fed by data points coming from some as an ID sample from some input distribution P, and you keep track on the MAP partitions or convex halves of clusters in this MAP partitions. You already know that those are disjoint, and you think you wonder if this picture somehow stabilizes as you infinitely increase the number of data points. And well, in order to answer this question, it was, at least partly, it was good to kind of reverse the optics. So now I start with some fixed partition of the observation space, and then throw my points randomly, independently from this input probability P on this observation space. And well, I can just read the partition. So in here, I know that what X4, X3, and X6 are in one cluster, one is in a singleton cluster, and so on and so on. And when I already have this partition, which is random because the points were random, I can ask what is the posterior distribution of this partition, but in the sense that in the sense of this Bayesian model I described before. So as I increase the number of data points, it turns out that I can compute, say, first order approximation to this posterior score of my random partition induced by this fixed partition A. First order approximation in the sense that the limit of the nth root of this posterior score. And in the end, it is a function which depends on the input probability distribution P and the division of the fixed division of the observation space A. So now there are two parts in here. The first one is just comes from the prior, the Chinese restaurant prior, and the latter comes from likelihood. And in here, it's just using the strong law of large numbers. That's it. And now it turns out that if every limit partition, every limit of this convex sets you see as convex halves of clusters of the MAP partition. Though we know that convex sets are, well, at least within a bounded settings, must have some limits, for example, in the Hausdorff sense. So every limit point of this MAP partition must be a maximizer of this delta P function. So this partition of the observation space you see here as a limit must be a maximizer of this delta P function, or with, unfortunately, quite limiting assumptions of this input distribution P, but well, we'll comment on it perhaps a bit later on. Now, switching to a more general setting, the first moment in which the easiest way to generalize this picture is to allow the covariance structure within clusters to vary. So now we may want to not only randomly pick a mean within a cluster, but also to randomly pick a covariance structure within a cluster from inverse Wishart distribution. And this is, again, a special case of conjugate exponential model. So let me name some parts of this expression that I use later on. So here I've got log partition function for the parameter, the log partition function for the observations, and the sufficient statistics for the observations. And this is the generalization of the likelihood. And now, as far as the prior on the space of partitions is concerned, we can concentrate on so-called exchangeable random processes. So a general way of describing them is, for example, to randomly split a 0-1 segment into subsegments. If I have got a way of randomly splitting the 0-1 segment into possibly infinitely many subsegments, then I can throw uniformly n points on this picture of this segment and just read the partitions from what I see in here. So this is, I mean, you can express, for example, Chinese restaurant process in this way, or pit manure process I'm using. Now, the first, in this more general setting, you can firstly extend the result concerning the separation of sets within the MAP partition. Namely, now the clusters within the MAP partition are separated by linear functionals of the sufficient statistics for the observation. So, for example, I mean, for linear model, as the sufficient statistics is also linear, then it gives you linear separation. But for this model where you can change the covariance structure between clusters, you obtain quadratic separability. So every two clusters in the MAP partitions are divided and are separated by a surface of order 2. Now, when it comes to this first order approximation to the prior I've mentioned before, you can also have this this convergence. Interestingly, this part coming from the prior on the space of partition remains to be this entropy looking part. I mean, no matter what exchangeable random partition you choose as a prior on the space of partition, in the end, as the first order approximation in this setting, you obtain the, say, entropy of this partition of the observation space. And well, this is, for example, what you obtain for this normal inverse Wishart model, in which, apart from this entropy part, you get the expected value of the logarithm of determinant of the covariance matrix of the, say, chunk of the observation space partition. Yeah, and what is worth mentioning here is that whereas within the fixed covariance setting, in this likelihood coming part, you obtained it depended on the specification of the theoretical covariance structure within clusters. Now, although when you specify this inverse Wishart model, you input the expected covariance with the cluster as a hyperparameter, this hyperparameter does not prevail in the limit. So in order to strengthen this prior information about what you expect as a covariance structure within clusters, we experimented with strengthening the hyperparameter of the concentration. So now, instead of keeping it fixed, we see what happens if the limit, if this parameter were to be changing linearly with the number of observations. So, well, this is how the formula is changing, and you can observe, I mean, obviously the part coming from the prior does not change, but you observe the change in the part coming from the likelihood. And yeah, this can be thought as a continuous transition between this case of random covariance where you have this concentration parameter fixed, and the case of fixed covariance mentioned before. And now, as we kind of approximating the posterior or the likelihood in this case here, and natural idea here, having this formula in front of our eyes, is to consider an empirical equivalent of this formula and use it as a score of some clustering proposals. So firstly, we may hope that an empirical equivalent of that one is a good indication of whether the partition is, well, better or worse. And secondly, I mean, many classical methods, k-means or hierarchical clustering, they need to specify the number of, they in fact produce a family of clusterings, and you need a way of choosing one clustering among them. So the idea is to choose an empirical equivalent of that one, where you just take the frequency of the chunk as an approximation of its probability, and the empirical covariance of the observation within the chunk as an estimator of its covariance matrix. And now, okay, the question is what to choose as sigma 0, and you can try to input here just the total covariance matrix. And thanks to it, you already know that as lambda approaches infinity, with putting here a total covariance matrix, you should well, underestimate the number of clusters, because in this case, it's just like you said that you'd like to see one cluster in here. And on the other hand, when lambda goes to 0, it's I mean, you may expect an overestimation. So it boils down to choosing the optimal lambda parameter in here. So it turned out that this method, I mean, gave you for some range of lambdas, gave you reasonable clusterings. For example, in here you can see k-means propositions for different case with 5 cluster data set. And well, the idea how you can use this empirical equivalent of this formula is just to score every proposition with different lambdas and try to read which proposition was the best in this setting. Okay, so now by looking at this picture, and maybe I too quickly scrolled through them, but a surprising thing is that, well, it's not very satisfactory, because in here we see 5 clusters, and from this picture you could think as the black dots represent the maximas, so the method should choose 3 cluster or 8 cluster solution. But another thing is that if you look at 3 cluster proposition in this case, not 3 but 5 cluster proposition in this case, the optimal one, I mean, you would like to see 5 clusters, but the method, I mean, it was just one run of k-means, and it wasn't optimal because it wrongly splitted that one and wrongly joined these 2. So actually this 5 cluster proposition wasn't good. So in order to investigate if this 8 cluster proposition was correct in some sense, we just measure its distance to the true partition which we know. And apparently in some sense this 8 cluster proposition was the closest one to the ground truth in this case, and this phenomenon was quite often observed in this in the simulations. Okay, so just finishing with things that may be done in the future in this case. So firstly, those convergence results I mentioned before, they do not work for fixed covariance model. So it would be nice to have the equivalent in, for example, normal inverse Wishart model. Secondly, I was considering the MAP partition, but well, there are more sophisticated ways of choosing a partitions in a Bayesian spirit, and it would be nice to have some similar analysis for them. And lastly, well, the usual million-dollar question, how to choose proper value of lambda. So thank you very much for your attention, and again for inviting me to give this talk.
Thanks also to Łukasz. Thank you a lot for great presentation. I don't see any question in the chat, and also due to time reasons, you will get a lot of questions, I'm sure, also from Julien and probably others. I suggest we move forward also to the final presenter, Théo. Théo will speak about on the use of a local R hat to improve MCMC convergence diagnostic. Théo, please.
Yes, thank you. Oh, okay. So hi everyone. Yes, today I'm going to talk about MCMC convergence diagnostic and about a new tool to improve how to assess convergence when we have MCMC chains. So basically, the aim is to when you have some posterior sample generated by your MCMC algorithm, is to know whether or not they are a good approximation of a sample that could have drawn from your real target distribution. So this is the typical setup for a MCMC algorithm. You suppose that you have multiple chains that you run in parallel, and then you can use the fact that you have multiple chains to be able to compare them and to help yourself to know if you have converged or not. Typically, the two main issues that you can see quite easily from chains that haven't converged is stationarity and mixing. So here I just plot two basic examples with two chains. In the second one, we can see clearly that the blue one is clearly not stationary. So as it's supposed to converge to a stationary distribution, it has a convergence issue here. We are still in the exploration phase. And in the last example here, if we look only at the green chain or only at the blue chain, you can conclude, you could have concluded that you have converged to the target distribution that you want to, but comparing the two chains allow to conclude that there's an issue because the two distribution doesn't have the same support, so the distribution is different and should have converged to the same thing. So you may have a convergence issue, and it's some example that appears in mixture model, for example, in case where you have multiple modes. But in general, one thing that you do is you want to compare the distribution of the different chains to conclude whether or not they are sufficiently equal to conclude that they all have converged to the same target distribution. And the most famous indicator that sums up this idea is called R hat, and it has been introduced 30 years ago by Gell-Mann and Robin. And the basic idea is to compute this quantity here, which is a ratio of W and B, where W is the within variance and B the between variance of the chains. So very briefly, if your chains contain your parameter theta ij, you consider that you have m chains of size n. I quickly write down the expression of B and W without looking very into the details of this formula. What you what is to remember here is that B is an expression of variance of means over the chains, whereas W is the contrary, it's a mean over the variances of the chains. If you look at a basic illustration here, using a toy example with only two chains that are really separated, here B is the mean of variance here. So no, it's a variance of mean, sorry. So the variance of the two means here is really huge compared to the means of the two variants here. So you will obtain a B that is way greater than W here. So in this quantity, R hat is always greater than 1. And over a given threshold, you can conclude that you have a convergence issue. And basically the threshold that is used is the 1.01. So yeah, I just write down the article, the reference of the article that suggests this R hat, that is just to show that it's really used in the Bayesian community. And recently, a new improvement has been suggested, and it's called rank R hat, and it's the common indicator that is used in a well-known library like STAN or PyMC. And it's something that is work like R hat, but it's just adding a layer of computation to avoid some false negative issues where you have some distributions that are not the same, but result in R hat equal to 1. So you are not robust to all the diagnostic of convergence issue. So the basic R hat and even the improvement rank R hat have still some limitation in the convergence diagnostic. And I will summarize those limitations and at the same time propose, explain what we are suggesting to solve them. And we start by this following observation that all those indicators does not target a specific quantity of interest, which means that you make these computations to conclude that your overall chains have converged or not. But in reality, what you do in Bayesian Inference is that you focus more on a specific quantity of interest. Let's say it can be the posterior mean, the posterior variance, the posterior mode. It can be some empirical quantile for confidence region, or even some more complicated functions. But basically, you can you may just want to focus on a specific region of your distribution, and if you're satisfied on this region, you don't need to ensure convergence everywhere. And based on this idea, we suggest to compute R hats not directly on the parameter theta ij, but instead on some Bernoulli variable indicator of theta ij less or equal than a given x. And so this R hat depends now on the quantile x that we choose. So we obtain a function R hat of x. So I just put a small example here with 4 different chains and a blue one that seems a bit different for the free over in green. So the basic idea here is to for every value of a quantile x here, compute the corresponding value R hat of x. And we obtain this curve that is shown here. And doing this computation has several benefits. The first one is that we obtain something that is local. So we can detect the non-convergence of the chains locally on a given quantile. The other advantage is that we compute R hat on variables that are Bernoulli variables that are indicator. So from a theoretical point of view, computing some mean and some variance could have we could have some issues about the existence of those moments if we deal with a Vittel distribution. Now that we have Bernoulli variables, we don't need the mean and variance always exist. So R hat will always have a sense. We can show that we detect many false negative. I will talk about this a bit after. And if we want to compare ourselves with the other scalar summary, the other R hat version, we suggest to consider the supremum over the quantile. So this is what we call R hat infinity here, and that I show here in the dotted lines. It is reached here in this region, in this quantile on this example. So we construct R hat infinity to answer this question of targeting a specific quantile. But another limitation that it exists, it was the robustness to certain type of non-convergence. And this is why rank R hat was suggested 1 year ago to be more robust to the traditional R hat. But we show that R hat and also rank R hat can be fooled with some constructed examples. So we did several experiments with some distribution that we construct by hands, but also with real Bayesian experiments. Everything is available online. We'll not go into the details of the experiment, but basically we can construct some examples where the chains are clearly different, but leads, when we replicate the value of R hats, of things that are near 1 for all the R hat indicators that exist. And in those examples, we are more robust to the others, diagnosing those convergence issues. So you may have to trust me a bit because I didn't details much this experiment, but everything is available online if you're interested. And if you have questions, I can answer in the end. The third issue is the lack of interpretability for all this diagnostic, because everybody makes some computation about R hat without focusing on the theoretical value R behind the estimation R hat. It just the heuristic is always based on at the estimator level, and it's difficult to know what is the theoretical value estimated behind, and what are, for example, the common properties of chains that leads to a same value of R, for example. And with our transformation, we have a nice properties that is thanks to the use of Bernoulli variables. The nice expression of expectation and variance of Bernoulli variable, which are really easy if we assume that each change have each element on a given chain have the same distribution fj. So it's kind of a stationarity assumption, but we focus on the mixing because we allow ourselves that each change have a different distribution. We know that the expectation is the CDF and the variance is f minus f squared. So from those formula, we can deduce a theoretical between variance b of x and within variance w of x, which is basically we find back here an expression of a variance of means here, and in W a mean of variance. And if we plug those theoretical B and W on the formula of R, we can deduce the population version of R hat of X, R of X, and this value is exactly what we aim at estimate using R hat of X. And we have this formula that depends only on it's an expression that depends only on the F value, the FK value. So we know exactly the statistic that is hidden behind what we estimate in R hat of X. And using this formula allows ourselves to study several properties of this expression. And one thing that we can do, for example, is using toy example where the computation of R of X is explicit. Here I put an example with uniform distribution. Compute the exact value R of X and the associated R hat of X to make some study about the biases, for example. This is something that we can do because the expression of R of X is available here. So in a way, we solve a bit the issue of interpretability with our version of R hat. And The other issue that exists for this convergence diagnostic is that you have to choose an arbitrary chosen threshold to conclude whether or not you have converged. At first, the first threshold that was suggested was 1.1, and then recent articles suggest that 1.01 are more efficient and more are better, basically to conclude that every chain that have a R hat over 1.01 haven't really converged. You can't really be satisfied with the resulting chains, but these are things that are really empirical. So for the choice of threshold here, what we have is a proposition that we have based. Yeah, I don't have a lot of time. So I'm going to be very quick under this proposition. This is just a result that we have. It's kind of a statistic test under a null hypothesis that all the chains have converged to a common distribution F. And if it's the case, R hat of X squared minus 1 converges to a chi-square distribution. And this term here is the effective sample size, the local effective sample size that replace basically the number of samples n times n, as we assume a Markov chain central limit theorem that replace a basic central limit theorem in the IID case. So we have this result of convergence under the null hypothesis, and this is something that we can use to define a given threshold associated to a given confidence level 1 minus alpha. And we have this formula for a given threshold associated to a given number of chain, a confidence level, and an effective sample size. I put some values here for a fixed value of ESS of 400, which is something that is suggested in the literature, a confidence level of 5%, and different values of number of chains. And what we see is that in the common configuration of m equal 4, 1.01 seems reasonable here, but we confirm it with our convergence property. But the problem here is that this result is only for R hat of X, and if we want a threshold for R hat infinity, we don't have any result of convergence of the supremum over the X. We need a stronger result of convergence over the whole empirical process. And so instead, we just did some replication to evaluate and estimate the threshold associated to a given confidence level. And what we conclude here is that for the same configuration, 1.02 may be a more accurate threshold here. So we justify our choice of threshold associated to our version of R hat. And the last point is it's one of the biggest issue here for this kind of for this convergence diagnostic is that we always deal with univariate parameter, and it's something that in Bayesian inference most of the models have multiple parameters, and if you want to diagnose parameter by parameter the convergence, you will never know the convergence of the dependent structure that is under all your parameter. You will only diagnose the convergence on the margins. So it's an issue that is kind of complicated, the generalization on multivariate parameter. And I can't detail this here, but we have we study in detail this extension in multivariate, and I have tons of slides after this one if you're interested, but I will not detail this here. But we have a preprint that is available online, and if you have any question, I will be happy to answer. Thank you for your attention.
Great, many thanks. A round of virtual applause. Actually, great presentation, and also again, due to time limits, we will probably go into the debates later. I provide now the place to Julien for the discussion. Julien Arbel.
Hi everyone. So let me find it. Can you see the discussion slides or not? Maybe no.
Yes. Yes,
you can. Okay, great.
Yes.
So let me see. Okay. So hi everyone. I'm Julien, also from Inria Grenoble as Théo, and yeah, I'm happy to discuss this session. So I find it really promising and also in a sense very healthy for the Bayesian community that that we are able to see such a variety of topics from Bayesian Inference, from Bayesian statistics, that is presented by young statisticians. So so let me recall that all of the presenters are either PhD students or freshly graduated ones. Okay, so my discussion is essentially structured as follows. I will start with just providing my view on the subject of approximate Bayesian inference, and then turn to the four presentations with somehow questions, or let's say general high overview questions or comments on the talks. So to start with, Andre and I constructed this approximate Bayesian inference webinar jointly, and maybe it's good to explain a little bit why we included talks in a apparently a sort of wider wider topics. So I think here we accepted the approximate Bayesian inference sense in a sort of very broad sense. So maybe at first, what we think about when we hear approximate Bayesian inference could be what I wrote this first bullet, like models where the likelihood is intractable. And so this is exactly what approximate Bayesian computation does. It solves it provides a solution for models where we can't evaluate the likelihood. So that's also called likelihood-free inference, like Lorenzo referred to it. And but this is probably more general than restricted to Bayesian inference, also simulation-based inference in a very general sense. We also wanted to touch robustness in the sense that the model we consider might not be well specified, so misspecification. The solutions to this include modeling like generalized Bayes or the posterior bootstrap introduced by Emilia. Also, we think, or maybe should I say, I think, I don't know, I'm not sure that Andre shares this this view on the question, but I feel that Bayesian computations, in a sense, is a solution to approximate Bayesian inference. So being able to sample the posterior by using Markov chain Monte Carlo, or we could also think about Hamiltonian Monte Carlo, or maybe Langevin dynamic ones, and so on and so forth. So as Théo spoke about, the question of diagnosing convergence for MCMC posterior sampling is one important issue in the field. And last, but probably also very importantly, I think Bayesian non-parametrics, as the subject presented by Łukasz, can be also included in that list. So actually in BNP, almost, well, some estimators could be obtained in closed form, but most of them require posterior sampling through some algorithm. And so, for instance, the map partition is one case where you just sample many times your different clusterings according to maybe a Gibbs algorithm, and then you select the one that the clustering or the partition that has come up the most in your posterior sample. So it's an example of a point estimator, and I might discuss this a little bit later in the slides. Okay, so let me go over the presentations one by one. Lorenzo introduced a likelihood-free inference algorithm, let's say, for generalized Bayes. So I like this idea of matching the two. So in a sense, I think some other instances, some other works also do match those two settings, but I like a lot how it's done here. It's presented, so it uses these scoring rules estimators, and then choosing a different scoring rule provides different types of estimators, and some are enjoy nice properties, some don't, some other don't. So for instance, Lorenzo, you you mentioned that you can recover Bayesian synthetic likelihood or BSL by choosing a specific scoring rule. So in case you can give in a few words the sense of what sort of scoring rule works for this, I would be interested. Yeah. You mentioned later, maybe I guess I should do all my questions. Just take a note of it, and I will give you the floor afterwards. Otherwise, my 10 minutes will explode. So then, Bayesian synthetic likelihood inconsistency. I was a little bit surprised to see this, but I assume I'm sure you're right with this. But I was wondering with whether some results from Chris Giovanni's team, let's say, actually corroborate this. I remember that BSL works well in the case of misspecification, for instance. So have you tried to apply? I see that you compare the different approaches you propose, for instance, kernel or energy score ones, in the case of misspecification. So could you also compare to BSL? Have you done it, and which one would perform best? That's the sort of questions I have. I think it's essentially this. So let me switch to Emilia. So Emilia spoke also about robust inference, but according to a different paradigm, let's say, that is based on weighted likelihood bootstrap. So a paper that dates back to the 90s by Newton and Raftery, and actually what she proposes is an extension of this WLB, weighted likelihood bootstrap, to the case, to what she calls posterior bootstrap. So it allows her to include prior information. So I was curious about it, but did not have the time to check. I was wondering, when I read this slide, Emilia, why, well, actually, what is called Bayesian in the original paper by Newton and Raftery, if in their approach, the prior is not used, or maybe what I guess is that it's not used in the same way as in your case, because I mean, it's not visible in the basic WLB algorithm yet that you present. But I guess that what I understand is that it provides a sort of approximate Bayesian posterior, but with no prior apparently, or maybe with a uniform prior. So another question regards the posterior bootstrap performance in the case of well-specified settings. I think you say that it works well So it clearly works well in misspecified settings, but then in the case of a well-specified setting, I didn't see, I think, a sort of comparison, like a numeric comparison, quantitative comparison with the fully Bayes inference. I would be interested about that, seeing this, and then I haven't seen much how you see your method, your posterior bootstrap, in the more general framework of generalized based or other robust methods. I think it's a question that is similar to the one of Amai a bit before. Okay, third talk was by Łukasz, and it's about a BNP approach to clustering, if we want. And I find Łukasz work in general, so he knows this. I find this work elegant in the sense that it provides nice information on the geometry of the maximum a posteriori partitions in BNP clustering models. And what I mean by geometry is, like, for instance, how the clusters are separated depending on which model is used, for instance. So in his talk, he started with the normal Gaussian model, and then is able also to extend to normal inverse Wishart 1. And well, I noted normal exponential, but maybe I got something wrong, I'm not sure, should check. The question, so I think he's aware of the first one, and actually that's something that Łukasz, you mentioned in your last slide. So actually the 0, 1, the map estimator, the map partition is the one, is a proper Bayesian estimator, I think, of the partition, and it's the one that is obtained as the minimizer of the Bayesian posterior expected loss associated to the 0, 1 loss. But yeah, the 0, 1 loss is maybe not very rich one. So as you mentioned, Wade and Garamani suggest to use the variation of information loss, and also quite many years before, people had mentioned the binder loss, like Mailer. So what I understand, and we've actually looked at the problem together at some point, this is turning all the computation very extremely more difficult, and that's probably difficult to say anything about this, but that would be extremely interesting. And the second and last point is, I'm not sure I've understood. So when you switch to different priors, so changing from the Chinese restaurant process of the DP, the Dirichlet process, to the one of the pit manure or Gibbs type or any other, I didn't get how it changes the geometry of the clusters of the map, how they separate. I see that you speak about the fact that they get separated as linear transforms of the exhaustive statistic in the exponential model, but I didn't get exactly how. Okay, and so last one was by Théo. So I should say that Théo is a student here at Inria. So most of the questions I could ask them directly to him, but I take the opportunity of the formal position that I'm in today to to ask questions anyway. And I'd be happy to see your point of view about these questions, Théo. So first, just a quick recap. The work proposes a local version of what is called errats. And one of the advantages that convergence or non-convergence can be detected locally, for instance, at quantiles. And there are nice theoretical results on this. For example, the convergence when n tends to infinity. So you mentioned the fact that with the original errata, the threshold is arbitrary. So 1.1, as it was in the first Gell-Mann and Rubin paper 20 years ago or 30 years ago, or 1.01 as advocated recently. Your proposal is that this threshold should not be arbitrary, but should depend on the number of chains, the level alpha that you have to fix, and also about the effective sample size. So my question is, what's your expectation about the Bayesian community adoption of this new rule that you propose a R-hat threshold that depends on all those things? And yeah, so that's actually a question that, so I'm a co-author of this work. And when I present this work, I usually get these questions. I give it to you as well. It's a bit of a shame that that's more for R-hat in general, not it's specifically for that one, but specific to us, because we adopt a frequency treatment like tests for a Bayesian question. And do you see any more elegant solution in the future? Okay, so I don't know, Andre, if I may use a few additional minutes, maybe, I guess.
Yes, sure, please just take
minutes. So I wanted to take the opportunity, since I'm speaking to an audience that is probably mostly made of young Bayesian statisticians. I wanted to advertise a few things. So one, maybe most of you are aware of, is the fact that there exists an international society for Bayesian analysis called ISBA. It's a really nice society, and actually the student membership is not too expensive, costs $5 per year. So what does it give to become a member of the society? Well, one of the things is that it provides a sense, a feeling of membership to a community, and it's nice. And also it provides the opportunity for applying to things like applying to travel grants, to conferences that are supported by the society, and also to awards. Like there are a number of awards for young Bayesians, for junior Bayesians. So this specific point leads me to speak about a section from ISBA. ISBA is divided into different sections. Some other sections include like objective base or non-parametric base or base computations and so on and so forth. But the junior ISBA section is probably made for you if you are a junior Bayesian researcher. So here is the link, and an announcement that dates back to today or yesterday that you can find on Twitter is that they are looking for new member positions like chair-elect and treasurer. So being involved in JISBA is pretty a nice opportunity for being involved in ISBA in general. And okay, lastly, since this webinar is about ABI, I wanted to mention the existence of this ABC One World seminar that takes place on a monthly basis, I think. And the next one is probably in a few days. I don't remember exactly, but it's going to be a really nice one. So you can go on this link. I think Andre might put the slides somewhere online, so you can also find the links. And with this, I wanted to close. So in case you are nearby Grenoble at some point, don't hesitate to come and say hi at Inria Grenoble. Thank you.
Thank you, Julien. Thanks a lot also for mentioning another One World actually seminar. So I open the floor to the speakers, probably in the line of the presentations again, to reply if you have to reply to Julien, maybe Lorenzo or anyone else.
Yeah, okay, I think I will start. Yeah, thank you very much, Julien, for the questions. So which current rule is the BSL object. He basically does. I can, if I can show my screen 1 second, that would be probably quicker to show. So it's this scoring rule here, which is called David Sebastiani score, and basically, as you know, in the Bayesian synthetic likelihood, you're assuming your likelihood to be multivariate normal, and you are estimating the mean and covariance metrics of that. So basically, this scoring rule is just the just the log likelihood of a multivariate normal distribution. And
okay, yeah, I see. Yeah, it makes sense.
Yeah, and why is it not proper? Is it the reason why it's not strictly proper? Is that it doesn't, well, it just considers the first two moments of a distribution. So if you have two distributions with, let's say, same first two moments but different third moment, it's not able to distinguish between the two.
Okay.
So, well, and this is why I was saying it's not consistent in this sense. So consistency, I meant if you have increasing number of observations, then the posterior concentrates on the true parameter value, or at least on a unique minimizer of the scoring rule. But if for a BSL, if you, for instance, the case I was considering, the GNK model is specifically a model for which you have some control on the third and fourth moments via the parameters. So you see this this phenomenon of the BSL posterior not being able to concentrate. Yeah, I think the results they have in the BSS literature is that basically, well, most of the results, they kind of assume the data to be multivariate normal. So this is why in their case it kind of holds. Yeah, and for BSL, for me specification, again, I don't really know much about that. Yeah, but I think I'm not sure. I think I'm not really sure what you do, but I think the argument again is that they may assume some kind of multivariate normality of the summary statistics at least. So yeah, that's my
makes sense.
My understanding of all of that.
Thank you.
No problem. Thank you for the questions.
Great. Maybe Emilia, do you have anything?
Hi. Okay, so thanks a lot to Julian for the interesting questions. And so I took briefly some notes about all these questions. So let's start with the one about why weighted likelihood bootstrap was considered Bayesian originally. So there are two reasons, I would say. So the first one is that Newton and Raftery proved the first order correctness. So in other words, they proved that if the model is well specified, then to the first order approximation, the asymptotic normality gives us the same covariance matrix as Bayesian inference does. And now there is another reason. So they didn't really consider that we should sort of use this algorithm itself, weighted likelihood bootstrap. What they say in the paper is that, okay, you can use weighted likelihood bootstrap on its own, but also you can use it and then correct it by a sampling importance resampling algorithm. So yeah, these are the two reasons, I would say.
The thing I don't quite get is where the prior appears in this.
It doesn't, but you can, but you can, when you have samples from weighted likelihood bootstrap, you can then, I guess, correct them and make them better. So that's the first approximation, and then, they argue that this can be computationally easier than running an MCMC algorithm, which I believe in certain cases that's true.
Yeah, because it's independent and so on.
Exactly. It can be done independently. And now the next question, that's really interesting one about posterior bootstrap for well-specified models. So I would say there are two sort of negative things and then a few positive aspects. So first of all, posterior bootstrap, as for posterior bootstrap, we don't really know how it behaves for small sample sizes. And that's when I maybe wouldn't necessarily advise using posterior bootstrap, because we don't know sort of how well it approximates the posterior. And I'm not aware of detailed work on theory on this. Another thing is that even when we do posterior bootstrap sort of correction on top of weighted likelihood bootstrap, it's still not second order correct. So it's first order correct in the sense that the first order Edgeworth expansion agrees with what we get from the posterior distribution, but the second order doesn't. So in that sense, even asymptotically, when we have many data points, maybe it's still sort of more correct to do the actual Bayesian inference. But there are advantages in the context of the hierarchical models that I mentioned during the talk and posterior bootstrap for modular inference. So in terms of hierarchical models, it may be quite unpleasant to run a metropolis within Gibbs for certain hierarchical models, and it just may be computationally easier to run posterior bootstrap for hierarchical models. Now, I would say, as I said before, maybe the biggest advantage is for posterior bootstrap for modular inference. And there are two sort of aspects. So the first aspect is computational. So when we do modular inference in the Bayesian sense, what typically happens is that we first run chain to get samples for θ1. And then for each of those samples, possibly, we run a chain targeting pi of θ2 given θ1. And now each of those distributions is different, so perhaps we have to tune it separately. And of course, we can use adaptive MCMC or something like that, but still we have a lot of chains to run and check diagnostics or do, some make sure in whatever way that all the chains have converged. Now, this is significantly simplified by using posterior bootstrap, because we don't need to do all those diagnostic checks. And one more reason.
Do you do it as well in 2 steps for θ1?
Yes. So what we do is that, we do posterior bootstrap for θ1 and then for θ2 given θ1. Now, another situation is, another sort of context of this is in terms of inference. So we proved in this paper with Pierre-Jacob that when we perform modular inference, it's no longer true, as we are typically used to in Bayesian inference, that credible sets are confidence sets when the models, well, in this context, both models are well specified. In other words, both models may be well specified, but still we don't get the right frequentist coverage. And we can fix this by using posterior bootstrap. So in that context, it is advantageous to use posterior bootstrap.
Okay.
Now, the first question was really great about comparisons to other generalized Bayes methods. So there are 2 sort of types of methods that come to my mind, and we have a comparison of those methods with posterior bootstrap. The first one is power posteriors, and the second one is so-called Bayes-back by Huggins and Miller. And so let us look at inference and let us look at prediction. So in terms of inference, as I said during the talk, there is a lot of this game between J2-1 versus the sandwich covariance matrix, whether they are equal or not. Now we know that in posterior, in the Bayesian posterior, the asymptotic covariance matrix is J2-1. When we use power posterior, it's a constant times J2-1. What we would want to have to get the right inference or the right frequentist coverage, we would want to have this whole sandwich covariance matrix. So a constant times J2-1 is generally not the sandwich covariance matrix unless for any constant, unless we are in the one-dimensional case or we are lucky with having everything right in the diagonal. So in that sense, weighted likelihood bootstrap is the only method out of those 3, power posteriors, Bayes-back, and weighted likelihood bootstrap, that gives us the correct frequentist coverage. Now, it changes quite a lot when we speak about prediction. So first of all, there is a theorem proved by Fushiki at the beginning of 2000s that when the model is misspecified, so basically this J2-1 is not equal to the sandwich covariance formula, and then we have better prediction under weighted likelihood bootstrap than under Bayesian inference. Now, what happens with the comparison with power posteriors and Bayes-back? So we show in our paper, and it's the first theorem in the paper, that, which says that
Emilia, I'm sorry to interrupt, just a little bit. Yeah, like 3 or 4 minutes more. So just
great.
I gladly borrow my time to Emilia, so because it's very interesting.
It's great to listen. Just thanks.
Thanks. Now I'm really just finishing. So essentially what we show is that if we either have over dispersion on all coordinates or under dispersion on all coordinates, then in terms of prediction, it's better to use power posteriors with a certain parameter or baseback. If, on the other hand, we have over dispersion on some of the coordinates and under dispersion on others, it's better to use weighted likelihood bootstrap or posterior bootstrap.
Okay.
So yeah, thanks, and that's all I wanted to say.
I hope you like your new life in Google, at Google.
Yeah, I do. Yeah.
Great.
Okay, I also want to hear about your view, Łukasz. I mean.
Yeah, so thank you, Julian, very much for the very nice presentation and the kind words, which I appreciate very, very much. And now, quickly responding to those two questions. Yeah, as you said, well, the question of analyzing the Bayes estimator of the partition when using binary loss of variation of information matrix remains elusive. Well, my intuition is that you cannot obtain an separation in this case, as I can imagine that when I've got several partitions which are convex, say in the sense that the convex halves of clusters are disjoint, then kind of the one that optimizes expected posterior expected value to all of them, to me not necessarily must be convex, but what would be very, very nice, and I guess this might be true, is to say that a distance of this optimal partition, in the sense that those spaces was to some separable clustering is small in some sense, but I mean the formulas are much more complicated in this sense, and the techniques I was using are not at all applicable in here.
Then if you think there is no possible separability in this way, do you see this as a drawback? Or because that would be, we expect these partitions to be better behaved, I guess, because the loss is like finer and so on and so forth, and that's also what is advocated by Wade and Garamani, I think. So how would you see this? And in that case, would you think? I mean,
certainly it is a drawback when it comes to the analysis of how it became. But as far as the interpretation is concerned, well, it's. I mean, most certainly the approach of Wade and Garamani is better. I mean, it's computationally more. Perhaps it's more difficult to pick those partitions that are optimal in this sense. But I mean, just like in the standard Bayesian setting, I mean the expected value of the posterior is a better estimator in the Bayesian sense that just the mode of the posterior, I mean, in terms of interpretability. I mean, the expected value seems to be a better summary of the posterior than the mode of the distribution. And now, as far as the influence of the change of the prior for the separability problems, well, the MAP may change, obviously, when you change the prior on the partition space, but it does not change the separability property. That's because, I mean, the reason for the separability is the fact that whenever you have any partition, you take two clusters and just switch observation between these two clusters. So you can prove that by doing this procedure, the best input of these two clusters into the posterior score are when those clusters are separable. So when you just do this switching procedure, it does not affect the prior, because for the exchangeable random partitions, the prior depends on the number of observations within each cluster. So this is, well, robust to the choice of the prior.
So with your derivations, what's the sort of change that you see when switching from DP to PY, for instance?
From switching from what to what? I'm sorry, I didn't hear.
To the research process to Pitman process, is it something
I see.
that you're
Yeah, I mean, for those separability results, there is no change, but unfortunately, there is a significant change when it comes to this these convergence results, which are useful in analyzing the consistency of the method, and even as slight, I mean, maybe not slight, because I mean the properties of the Pitman process are obviously different from the properties of the Sisson process, but even introducing this additional parameter causes some, I mean, some limits, some expressions are not bounded then, and you cannot perform the same analysis for the Pitman process when it comes to convergence as you do for the Dirichlet process. But those results, when it comes to the limit of the posterior score of the induced partitions, I mean, this does not change, and it's universal in terms of the prior on the partitions. So, yeah.
Okay, well, thank you.
Thank you very much.
Same as for Emilia. I hope you enjoy your new position at Warsaw University.
That's correct. Thank you.
I guess it's my turn to answer briefly on the question that you asked. So the two questions was, one was about choosing a threshold for our convergence diagnostic, and is it how it's going to be received that we have a threshold that depends on the number of chains, the confidence level, and effective sample size, having those kind of hyperparameter or something that will change the threshold. And the second question, I think I will start on this one, was about a more Bayesian way to diagnose convergence, because what I present here was looking like a bit a statistical test. I think at first the heuristic was more Bayesian, because the ratio that I presented here on R hat was based on a ratio of two quantities that aims at estimating the posterior variance. So the heuristic was saying we have two quantities that estimate the posterior variance, one that overestimates and one that underestimates, and doing the ratio leads to something that is greater than one. And if you have this quantity, which is the posterior variance, that is estimated correctly, you can be satisfied with your MCMC chains. But it's something that's maybe there's something more elegant to do rather than just computing a ratio of two quantities that you estimate. This is, I think probably, but what we did, so I said we because you work with me on this, maybe it's do this bridge between this Bayesian point of view of having those posterior quantities that you those posterior variants that you estimate and the ratio that you compute about those estimator, and over more traditional frequentist result like the Kolmogorov-Smirnov test. These are kind of things that are done in the frequentist world, where when they want to compare the distribution. And I guess we are in the middle of both, but maybe there's something that is more Bayesian to do. Yeah, probably. And about the threshold that depends on the number of chains, the effective sample size. I think there's another R hat that I didn't mention that was suggested by Dutika Vats and Christina Knudsen in 2019. That had a threshold that depends on the number of chains. I'm not sure 100%, I have to check, but I'm not sure. I don't think I'm the first one to have this. So I don't know. I don't really know how it's going to be received in the Bayesian community. I guess having a clear expression like the one I have for R hat of X that is totally explicit may be fine if you have the configuration that you chose at first when you run your MCMC. But then having to estimate it using replication can be an issue if you don't have any general expression of the threshold in the case of r hat infinity. But I don't really know. I don't really know how it's going to be received.
You will have a reply to this question at ISBA meeting in 2 weeks.
Yeah, I hope so.
If people are throwing tomatoes to you, that's probably bad signal. Okay. I didn't ask the elephant in the room question about multivariate.
So there's this question, but I also wanted to, there's someone in the chat who asked me a question, but it was in private, but I wanted to mention it too because it was an interesting question about if I had any insight about the choice of the number of samples and the number of chains. And the answer is no. So I don't really know. Like the number of samples, of course, if you can have as many samples as you want, try to have the, if you don't have any computational issue, the longer the chains are, the better will be your approximation. And basically a number of iteration that leads to r hat that is low is fine. But then for a fixed number of iteration, let's say if you have 10,000 iteration, do you prefer to split it in 4 chains, 5 chains, 10 chains, or maybe 2 chains or 1 single chain? It's something that I don't have real insight on this. And I guess it's kind of, it's part of a big debates that exist in the community since several decades about whether you run a single long chain or multiple more little ones. And I guess now for computational issue and with the raising of parallel computing and everything, maybe you can try to run more chains in parallel if that facilitates the computations. And maybe
the answer to the question is clearly conditional on whether you can do parallel computation or not.
Yeah, exactly.
Cool.
So yeah, that was my answer for that.
Okay, thank you.
Great. Great, thanks. I suggest we open now the debate to the public, the ones who remained. If there is any question, please feel free to unmute or write it in the chat. I will start with a few of mine. I will post 3, there will be more, but I'll leave it to 3. Firstly, for Łukasz, I have a question. Basically, Julien explained in detail the connections between the talks, but would it be possible in your case of clustering that you explained and so on to come to situations of likelihood-free methods, so of approximate, of intractable likelihood, and so on? Could this be met there, and how to tackle it? Basically, shortly from Théo, you mentioned problems in terms of the convergence of the R infinity related to the problems of empirical processes. Could you explain this in a little bit more detail? What is there in the asymptotics? And finally, for Emilia, shortly, our next webinar will be about econometrics in 2 weeks and so on. And you probably know, you all know that bootstrap is highly frequently used also in econometrics, but frequentist versions. What would you recommend to econometricians in terms of those similarities? Could the posterior bootstrap, would you recommend it to them, and in which situations? Thanks, this much.
Okay, so probably I should start in the sense that I was asked first. Well, this topic was connected to the approximate Bayes in the sense that at some stages I used this first order approximation to the posterior, but as far as the true spirit say, I mean, I also share the view that it's still connected, but as far as free likelihood is concerned, well, I was I went a convenient path for me, because I only considered conjugate exponential, in which you can compute the marginal likelihoods, I mean, in this case for the observations. Now for the models in which you cannot do this, well, certainly you can try to analyze the formulas for this free likelihood. I haven't done this, and yeah, it remains a good idea to investigate, especially after the wonderful talks we had before.
Great, thanks.
So I think it's my turn to answer the question, but I'm going to share my screen. It's going to be easier for that convergence issue about R hat infinity. So just it's a reminder of the population version R of X, and just what I wanted to show is that if all the distribution are the same, this expression is exactly equal to 1, because this is equal to 1, and then the threshold this result of convergence that we have here is like under the null hypothesis that all the chains have converged to the common distribution, and so R hat of X minus 1 converges to the chi square, but it's something that is for any X in R. And the threshold that we have, this expression that we have here, is based on this convergence result under the null hypothesis. And the thing is, this result is kind of a result of weak convergence, because we have the convergence for any X, but we can't just write a supremum over the X in this formula really easily, because we don't have the convergence of the whole empirical process R hat dot, but just a weak convergence over the whole X. And in fact, the supremum here does not converge. R hat infinity square minus 1 does not converge to a chi square anymore.
Okay. Do you have any idea how to study them?
Yeah, so I guess one way to study them is maybe using like a Donsker theorem instead of the central limit theorem, something like this.
Yes.
But I wasn't able to finish the computation, like to succeed in something. But I guess it's possible. It's for future work, to be honest.
Thanks.
So I believe it's my turn now. Thanks a lot for this question. So it's really interesting. So first of all, in terms of similarities between Inference bootstrap, where we sample with replacement different data sets and perform computations and sort of put them together for the whole sample, and Posterior bootstrap. The similarities are that we can run it in parallel and that we have the same first order approximation. So we will always have this right frequentist coverage. Now, in terms of differences, I would say that the advantage of using Posterior bootstrap is one of the general advantages of using Bayesian inference over frequentist approach. That is that we can use and introduce appropriately mathematically the prior information. And also we can do it when the prior has a hierarchical structure. And another aspect of this, and there is a really good paper on this topic by Fushiki from 2010, if I remember correctly, is that when we have a small sample size, there may be numerical issues with performing Inference bootstrap, because, for example, when we have a regression, finding the coefficient beta in regression requires inversing a certain matrix. And if we remove, say, if we sample with replacement, we may get such a data set that the matrix is not invertible. So this is not the case for weighted likelihood bootstrap or Posterior bootstrap, because generally we'll be able to avoid this problem. And also we have, in the same for the same reason, we have a more sort of smooth distribution of the samples that we obtain from weighted likelihood bootstrap than Inference bootstrap. So So I guess this is the main sort of comparison of of differences and similarities. Thanks.
Great. Many thanks. And we have one question in the chat, which is for Théo. We just arrived. Mehdi, you can unmute, or I can ask it.
I can read the question.
Okay.
In the multivariate case, does the nature, for example, real versus binary of the random vector of interest have any effect in the MPSR F value? In other words, does it provide similar convergence diagnosis result regardless if the vector is real or binary? That's a good question. Okay. I think, so keep in mind that in our version, we never compute R hats on directly the parameter, but rather on the indicator. But this indicator has to be computed over quantiles. And so does it make sense to compute? So we only focus on, we never focus on discrete parameter, but only on real parameter. And I guess it can work in the discrete case, but I'm not really sure, because like in any case, when you compute those quantities, you estimate them using some empirical CDF, and basically your indicator function will be computed in a finite number, in a finite grid. So I guess it doesn't change anything, but does it have any effect on the MPSRF value? So I guess, so yeah, there's two things. Like this issue can also happen in the univariate case. And in the multivariate case, so I didn't mention the multivariate case, but we still have some issue regarding the direction of the dependent structure. It's a bit similar to the Kolmogorov-Smirnov test, if you're aware of that, is that depending if the dependence is positive, negative, or neither of them, we are not sensible in the same way in all the direction. If we consider just the simple generalization, like the most intuitive way to generalize our diagnosis in the multivariate case. So anyway, even in the in the simplest case of real parameters and not binary or discrete, we already have some issues in the multivariate case. But yeah, that's a good question. Thanks for the question.
Great. Anything further? Any further question? Participants, please feel free to unmute and ask. If not, I thank greatly to all the speakers, excellent presentations, to Julien for his great discussion, and to all the participants who came. The webinar was recorded and live streamed. It is probably already online or will be online in a few minutes, and then put also formally on the YouTube channel. So thank you greatly. We continue in 2 weeks, as I mentioned, with a webinar on instrumental variable methods with forum econometricians and Peter Hall as discussant. So thank you a lot again, and see you probably soon in my name, I will say, in Bayesian circles. Thank you a lot.
Thank you, Andrei, for organizing.
Great.